a short conceptual review, and then we'll be moving on to covering the problem. So with that said, we'll just get right into it, starting with problem 1.
Okay, so I'll be going over kind of the background of problem 1, like Poojan just said. So I'm just going to share my screen with the notes that I've taken, and we'll kind of walk through it together. Okay. Can you let me know if you see my notes?
Yeah, you're good.
Okay, perfect. So I guess some of the main concepts. Okay, some of the concepts that this problem entails are thermodynamic cycles, state functions, the standard state definition, and then the free energy formation and how it relates to equilibrium. So to start with the first one, a thermodynamic cycle kind of breaks down a reaction. So for example, in this picture that I have, this one specifically is for the glucose formation. So one way I kind of thought about it is if you're thinking about like making a cake, you're not just going to add like flour, sugar, eggs, water, like throw it in a bowl, and then it won't just become like a frosted cake. It has like different steps to it. Like first you have to use like the flour, water, eggs, bake it, and it'll be a cake. And then you can have like your sugar, eggs, make your frosting, and then you put like the cake and the frosting together, and then you have your cake. So similarly, like a thermodynamic cycle like breaks down like these steps in the creation of something. And if you know like the delta G free energy for like certain parts of it, then it's kind of like a puzzle where if they give you 3 of them, you can figure out like the 4th like missing value. And so this is just the textbook definition. So it's saying that there's 2 different pathways that connect the same set of reactants and products with the same starting and ending conditions. And then the change in any state variable, such as the free energy, enthalpy, or entropy, must follow that pathway. Yeah, so I guess that's kind of my intro on thermodynamic cycles. Does anyone have a question on this part? Okay, so I will move on to state functions. So this one's also pretty much just a definition. Some examples are delta H, delta G, delta V, delta T. So these are all properties of the system that are independent of the history of the system. And these are all things that the thermodynamic cycle is going to help you like calculate or figure out. And then an example of a path function, so things that wouldn't work for thermodynamic cycles are work and heat. And standard state definition is pretty standard. It's just telling you that it's kind of like the convention. So in biochemistry, it might be different from like physics, like what they might use for standard state. So for like this class, like for water soluble molecules, the standard state is usually 1 molar at 1 atmospheric pressure. Concentration of like hydrogen ions is like 10 to the negative 7 when you're calculating for pH. So it'll just be like the definition. And I think for most of Korean's exams, he always tells you what standard state is, so you shouldn't have to have it memorized, or you can just add it to your cheat sheet. And the last concept is the free energy of formation and how it relates to equilibrium. So delta G is, as you know, the molar free energy upon change upon the stoichiometric conversion of reactants to products given their actual non-equilibrium concentrations. So I liked this graph that kind of looks like this kind of a parabola. And I guess some questions that I wanted to just ask you are like, what would the delta G at equilibrium be? You can just shout it out because it's also kind of there.
0.
Yeah, exactly. So it's 0 because when you're at equilibrium, the forward reaction or the backwards reaction, both of them are not spontaneous because you're at equilibrium. So then basically the delta G value is telling you where the equilibrium like would be, what reaction would lead you to equilibrium. So if delta G is negative, it means that the forward reaction is favored. If the delta G is positive, it means that the backward reaction is favored. So this graph kind of shows how that works. Any questions on any of the concepts that I've kind of gone over so far? If not, I will turn it to the next tutor to go into the actual problem. Okay, I will stop screen sharing. All right, and then whoever's taking over for the actual problem, go for it.
Yeah, okay.
Okay, so I'll be going over question 1. And so in part A, we're asked to draw out a thermodynamic cycle that, so it's similar to what Niti just showed. And we will start by identifying the starting elements and also the final products. So we're giving A, B, C, D 4 elements, and we want to find the thermodynamic cycle for the formation of E. So we know these are our starting reactants, and we want to find the thermodynamic cycle for formation of E. And so if we look at these 3 equations, the first one tells us A plus B equals will give us Y, and then the second one tells us C plus D equals D, and then the final one tells us Y plus C equals E. So then we can draw the next step, which is which will just change our molecules to Y plus C plus D, because A plus B will give us Y. And during this process, we will have a change in free energy of Y formation, which we can denote as delta G of formation of Y. And that's following this equation. And then if we go with the next equation, we will get Y plus Z, because C plus D equals Z. And we can denote this process, the changing free energy of formation of Z. Oh, yeah. And then we can go with the third equation, which is just Y plus Z equals E. And this process will have a changing free energy formation of E. And just for completion, we can denote this entire process as the changing free energy for the formation of E. So this is the thermodynamic cycle for the formation of E from the elements A, B, C, and D. Is there any questions on part A? Okay, so then for part B, we're asked to find the changing free energy formation for elements for the molecule E, which is the one here. And as Niti just said, the changing free energy formation is a state variable. So we only care about the starting reactant, and the final product. And it doesn't matter which path we take. So if we look at this cycle, it's the same if we go with this path, and the same if we go with this path. So and we can see with this path, it's just the sum of changing free energy of Y and plus changing free energy of Z and changing free energy of E. So that would just be the sum of this. And we can see from the table that we're given these 3 values. So this one will be -100, and this one will be 120, and this will be 40. So you guys can just plug in the numbers and find the free energy formation, changing free energy formation of E. Is there any questions about question 1?
Hi, I had a question about part A.
Yeah.
So in this one, you drew that you form Y first. Would you also have to draw like the cycle that forms Z first? So it'd be like A plus B plus Z.
I think you can draw it either way.
Okay.
Yeah. Because E is just from, yeah. No problem. And if you have any questions, feel free to message me privately through the chat too. And we can move on to question 2 now.
Right. Let me just get ready here. All right. I'm sorry that my video is really blurry. I'm not sure what's happening about that. I'll just try and write dark. But I'll be covering some concepts on chemical potential. Let's just dive right into it. Okay, that's a little better. So we can define chemical potential of mu of some region or number of molecules I as the change in free energy, dg, divided by the change in number of molecules in that region, dn, when we hold temperature constant, pressure constant, and if we're comparing two regions, the number of molecules in the I region is not equal to the number of molecules in the J region. So we define it basically as a free energy change per molecule. So in this form, we have units of joules per molecule. And we can also write, which is more common, what I think you'll be seeing more of, the molar chemical potential, which is simply similar, except we're dividing by the number of moles n. Same thing here. This has units of joules per mole, and you can convert between these two by multiplying by Avogadro's number. I'm sure you're all pretty used to that by now, but just make sure you know what units you're looking for depending on what problem you're doing. Now I'm just gonna set up a box real quick. So let's pretend we have a region inside this box. And there's molecules all around here. I'm gonna denote this inner region as just in, outer region as just out. And let's pretend this system is at equilibrium. So we have a bunch of molecules bouncing into this box, out of this box, but it's all in equilibrium between the inside and the outside of this dotted box. So we can write the free energy change, total free energy change, as the sum of the energy change of the inside plus the sum of the outside. And we know at equilibrium, our free energy change total will be equal to 0. Now we can plug in from above, plug into here, and I'm just going to use molecules for now. Say dg is equal to mu of the inside times the change of number of molecules in the inside plus mu of the outside times change of molecules outside equals 0. Now we know we can say this relationship, number of change of the inside is equal to change of the outside. And what this is saying is just a coupling thing. We know if, let's say, 5 molecules entered the inner box, we know there has to be a decrease of 5 molecules from the outer box. That's all that's saying. If we were to plug this in, we now get mu in, dn in, minus mu out, negative sign, dn in again, equals 0. Let's factor this. Mu out, dn in is equal to 0. We know this cannot be equal to 0 because we need a finite number of molecules. So our quantity here must equal 0. So we know at equilibrium, mu in must equal mu out. Now from here, so this is at equilibrium. And let me move this up slightly. Okay. Now let's pretend instead of our being at equilibrium, we had a delta G that was less than 0. And the number of molecules inside the box were greater than the number of molecules in the outside of that box. Now our inequality from before changes to this. dn in is now less than 0. So if we have more molecules inside the box than outside the box, we know from diffusion that the molecules are going to diffuse out of the box. So dn in has to be negative, right? Because we're going to have molecules exiting the box by diffusion, which means mu in minus mu out is greater than 0. So mu in is greater than mu out. And all of this is saying is just molecules will go from high potential, so greater mu, to low potential. That's all this is saying, but just in a more mathematical sense, if that helps you in any way. Are there any questions about this? I will take that as a no. Let me just flip this over. 1 second. And we'll go into a derivation of an important equation you'll be using on the problem set. So let's take this time 2 separate regions. Oh, can you see that? Okay. Sorry, my camera is really laggy for some reason today. So let's just call this region 1, region 2. And this is going to be an ideal dilute solution. Ideal solution. And in region 1, we have n1 number of molecules with m boxes. And then region 2, same thing, except n2 number of molecules, m boxes. So let's calculate the change in potential for this. And we can do that by saying delta mu, which is mu2 minus mu1. We can say this is actually equal to just from before the change in free energy per molecule between each region. And we can actually substitute in for this expression dg is equal to dh minus t ds. So this is just your Gibbs free energy equation, except with derivatives. We can plug in into this equation. We'll get dh2 divided by dn2 minus t ds2 dn2. Simple substitution, do the same thing for the other side. T ds1 dn1. Now we can actually simplify some stuff because we know this is an ideal dilute solution, meaning there's so few solute molecules bouncing around in that solution that our enthalpy change can actually go to 0. So these terms, dh2 divided by dn2, will go to 0. Same thing for the first region. And you can read more about ideal dilute solutions on page 416 if you want to see more of an explanation on that. But this simplifies our expression now, because now all we're left with, if we factor out some stuff, is just the entropy terms and temperature. So we're here. Now, you can actually use the probabilistic definition of entropy that you learned. I probably spelled that wrong, that's okay. Probabilistic definition, which, if you need a reminder, is S negative KB T PI ln PI. And I'm not going to go through all the math because it will take a long time, but you can look on page 419 and 420, especially box 10.1 in your textbook, if you want to see exactly how you simplify this down. But basically, this will yield us to delta mu, it's kBt, times the ln of n2 divided by number of boxes, m, minus same thing, except with 1, divided by m. And from here, we can simplify this using concentration and substituting in for m. So we can define concentration as number of molecules divided by volume, right? And we also know that m can be equal to alpha times volume. If you plug these in for both n2, n1, and also the remainder m's, you'll get this fun equation, kBt ln C2 divided by C1, which you will be using on your problem set. I don't think you'll be required to know these proofs, but it'll be good to look them over, understand that this equation is coming from simply a change in free energy, right? A change in free energy. Are there any questions about that? All right, I guess Shivani can jump into the actual problem then.
All right, let me get my screen ready. Okay. Let me know if you can hear me and see my screen, okay? Anybody? Mhm. All right, can everybody hear me? Yes, okay. Okay, so using what we just learned about chemical potential, now we can go into problem set question 2. So question 2, part A, basically describes a solution with 2 regions, region A and region B, with a 5 kilojoule per mole difference in between them, difference in chemical potential in between them. So there is a 5 kilojoule per mole difference in between these 2 regions. Now, it's important to note that this is an ideal dilute solution, meaning the enthalpy term, as Chapin mentioned, goes to 0. And so since the solute doesn't interact with itself, the changes in free energy are directly related only to the changes in entropy, and therefore to the change in concentration. So in an ideal dilute solution, since systems favor going from high energy to low energy, the molecules travel from a region of high chemical potential to low chemical potential. So high chemical potential indicates that the region has a higher concentration, and low chemical potential means that it has a lower concentration. Now, in this case, we don't actually know the exact concentrations of region A, but we are given that region B has a higher chemical potential. And so we can assume that the concentration in region B is higher than that of region A before they equilibrate. So given the fact that molecules travel from a higher chemical potential to a lower chemical potential, which direction would be favored for the net travel of molecules? Someone just shout it out. Which of these directions?
To A.
Left.
Okay, yes, that's correct. So it will go in, so more molecules will travel in this direction. So from region B to region A. And remember that the movement of particular molecules in this case is random, but the net movement of molecules is what we're concerned with. So the net movement of molecules is in the direction from region B to region A. And from that, we can figure out whether the concentration of A will increase or the concentration of B will increase. Okay, so does anyone have questions about that? All right, we can move on with part B then. Okay, so part B asks for the concentration in region A at 300 kelvins. Now, this concentration refers to the initial concentration in region A, so before the molecules have equilibrated with each other. And so that means that there is a difference in chemical potential in each region. So, and we're given this difference in chemical potential. So if we know the concentration of one region. So we know the concentration in region B, and we know the difference in chemical potential between the two regions, then we can use the equation that we just derived, which is delta mu equals RT ln concentration 2 over concentration 1. So this is the difference in chemical potential. So and in this case, we're given the concentrations in molars, so we would use R instead of KB. And so when we use this equation, sometimes it's confusing to determine which concentration in this case is C2 and which one is C1. So a simple way to determine this mathematically for any situation is to just check the signs of the equation. So if you use a change in chemical potential equal to, or a difference in chemical potential equal to 5 kilojoules per mole, and this side of the equation would be positive. That means that ln of C2 over C1 is also positive, and that means that C2 must be greater than C1. So we know that C2 is going to be the higher concentration, and C1 is going to be the lower concentration. And we know from the difference in being given which regions have a higher chemical potential and which ones have a lower chemical potential, we can figure out which one has a higher concentration and which one has a lower concentration. So, so region B we know has a higher concentration to begin with, and so we can substitute this with the concentration in B, and then we can solve for the concentration in region A. So yeah, basically you can just plug in the values that we're given now to solve for C1 right here. Are there any questions about that?
For RT, would we just use 2.5 kilojoules per mole?
Yeah, you can use the shortcut you're given because it's assumed to be at 300 Kelvin.
Thank you.
Yeah. Mm-hmm. Okay, if there are no more questions, we can go to problem 3. So let me stop sharing my screen.
Okay, hi everybody, my name is Byron. Before we go into question number 3, I'm going to give you guys a review on statistical and probabilistic definition of entropy. So let's first remind ourselves about this definition of multiplicity, which describes how many ways you can achieve a certain macro state. It tells you how many micro states there are within a macro state. So if we have n atoms in total, you'd have n factorial over the atoms in state A factorial, number of atoms in state B factorial, and so on and so forth. And this formula basically gives you how many ways you can achieve a macro state. So if we have one particle and if we have a box just like this, and if we say, okay, let's divide this box into 2 parts. The first section we call it A, and the second section we call it B. So the molecule can have 2 states. It can either be a A-type molecule, which means it's on the left, or it can be a B-type molecule, which means it's on the right. So in the first type of macro state, what we have here is our A type of molecule is 1, and our B type molecule, oh, let me actually change the pen type, and our B type molecule is 0. So if we calculate the multiplicity of this macro state, it is 1. And if we do the same thing for the second box, now we don't have any A-type molecule, and we have 1 B-type molecule. And if we calculate the multiplicity for this macro state, it is also 1. So we come to the conclusion that these two macro states are equally likely to occur. So what if we increase the number of particles that we have? So we still have the same box, but now let's consider 2 particles. So in this case, we will get 3 different macro states. However, now these macro states, one of the macro states is more likely to happen than the other 2. So let's look at the first one and the third one first. So we have 2 particles, and both of these particles are A-type particles, which means they're both on the left, and we have no B-type particles. And if we look at macro state 3, we have no A-type particles, and we have 2 of the B-type particles. Oh, I'm sorry, 2 of them. And we only have one way to achieve either macro state 1 or macro state 3, because if we calculate the multiplicity of each of them, it's both equal to 1. However, if we look at macro state number 2, we can have 2 equivalent ways of achieving it. By that, I mean, if you start with macro state 1, you say, okay, let's try to change it to macro state 2. We can put the first molecule into this A section and this molecule into the B section, or we can put this first molecule into the B section first, and then put this second molecule into the A section. However, when we achieve macro state number 2, you would not be able to distinguish between these 2 macro states because we have the same type of molecule. So these 2 micro states are equivalent to each other, and it can be calculated, the number of these 2 micro states can be calculated with the multiplicity formula. So in this case, we will say macro state 2 is more likely to happen. What if we increase the number of molecule even to a higher number? If we have here, if we have 4 particles.
How long is this going to go for?
Exactly. So we will have more macro states. We now have 5 macro states. And then if we calculate the multiplicity for each macro states, we will find out that number 3, macro state number 3 has the highest number of micro states. So you have 6 ways to achieve macro state number 3. However, you only have 4 ways to achieve 2 or 4, and you only have 1 way to achieve either 1 or 5. So statistically speaking, macro state number 3 is more likely to happen. So if we go to 10 particles, you calculate all of them, multiplicity for each of the macro state you can get, you will find out that the circled macro state is the most likely. So in your textbook, if you look at the coin tosses, well, you increase the number of coin tosses, you will find that the multiplicity goes really high. If you compare them, you would see if you do 1,000 coin tosses, you get a very, very high multiplicity for when the number of heads equals to the number of tails. And that macro state of 500 head and 500 tails has the most number of ways to be achieved. And you have 10 to the 300 different ways to achieve that macro state. And statistically speaking, it is more likely to happen. And therefore, we define statistically, entropy is the measure of the number of equivalent microstates. So we write this by S, which is entropy, equals to a constant. In this case, is the Boltzmann's constant times the ln of W. And as you can see, if we increase W, which is the multiplicity or the number of the equivalent microstate, you would also increase the entropy. So let's take this in. Are there any questions? Okay. So now we have some understanding about statistical definition, the statistical definition of entropy. Let's move on and see the similarity and differences between the statistical definition and the probabilistic definition. So now if we have another box going right here, so now we have a bigger box, okay? It's longer. We divide it into different sections. And if we have 1 to T sections, and we would call molecules in T section as the number of molecule in T section is NT. So for example, if you're counting the molecule in section 1, we would call it N1. If you're counting the number in section 2, we call it N2. And the total number is N. And if we assume N and NT are both large, we can write down this formula to calculate multiplicity for a specific macro state. So since N and NT are both large, we can use Stirling's approximation. So if we just take a part of this multiplicity formula in factorial, and we apply Stirling's approximation, what we can do here is n factorial can be written as equal to e to the ln of n factorial, because these two can be canceled. And since n is large, so we can use Stirling's approximation, and then we can write e to the n ln n minus n. And this is equivalent to e to the n to the ln, n ln n over e to the n. And then we find that these two n's can be taken out of this parenthesis. And then what we do is we would simplify by canceling e and ln on the top. And then in the end, we get this formula. So we approximate n factorial to be n over e to the n. So if we call this equation 3, and then this is equation 1, now we combine these two equations, we can approximate all of these terms. And what we get is this multiplicity, if n is large, will be approximately equal to this big formula. And if we do some algebra, we take this e to the n outside of this parentheses. And if we take this n1 to the n1, n2 to the n2, all out of the parentheses, we get this. And then notice that every single term has a e, 1 over e to the n. So if we take all of them out and we add up all of their power, they end up being the total number of molecule. And then we can cancel these two terms. So we get formula number 4. And then if we define the probability of finding an atom in the J's state, so if we go back to this box, for example, this is one of the J, this is another J, all of them can be called J. So we define the probability of finding one molecule in the Jth state is Nj over the total number of molecule. We can do a little bit algebra on equation number 4. We can write it as n1 over n to the negative n1, n2 over n to the negative n2, so on and so forth, so that we can substitute this pj, and what we get is multiplicity can be rewritten as this formula, number 6. So p1 to the negative n1, p2 to the negative n2, so on and so forth. And if we take the logarithm on this equation number 6, what we will get is this formula. And then if we divide n on the outside, divide n on the inside, I'm sorry, and times n on the outside of the sum, what we get is this formula. Now we have rewritten the multiplicity. We actually approximated with Stirling's approximation and then rewrite it in this form. So if we remind ourselves of the definition, the statistical definition of entropy, which is S equals to KB times Ln W, if we substitute Ln W with what we just came to, what we will get is negative NKB times the sum of the probability Ln and the probability. So let's get a very fast understanding about this formula, so what will give us. If we just look at Pi times Ln Pi, and remember these probabilities, we want them to be true probabilities, so we normalize them. Which means if all of the probability adds up, they should equal to 1. That means each of the Pi should never exceed 1. So I have drawn a line right here. If I redraw this graph, what we should see is something like this. So the dotted line are not allowed. And if we now take this negative sign into account, so if we take the negative sign into account, what we will see is we will basically make all of these negative values to be positive. So if we imagine a situation where we restrict all of the particles to box A, and that means PA equals to 1. and PB equals to 0, all of the P equals to 0, PT equals to 0. What will happen to that is your ln PA will equal to 0. And then PI ln PA will also equals to 0. And then negative PI ln PA ln PA will also equals to 0. And for all of the other terms, for example, PB and to PT, all of these terms will also equal to 0 because we cannot find any molecule in those boxes. So in this case, our entropy is 0, which is a very organized macro state, and probabilistically speaking, it is very unlikely. So in question number 3, you'll be using this boxed formula right here to figure out the entropy of the system. Okay, so now, do you guys have any question on the definition of entropy? Okay, so now I'll pass it through to James.
Okay. Does anyone see the page on the Zoom meeting?
Yes, it's good.
Okay. So, okay, I'm James, and I will be covering question 3. So question 3. So if by reading the question, we know that every grid box is occupied by type A or type B molecule, and there's no empty grid box. And there's no difference in interaction energy between A, B, and AA and BB pairs. So now let's read a question. So part A, so what is the entropy of the system when it contains only A molecules or only B molecules? And the assumptions here is that the first, there's no empty box, which suggests that if it's only A molecule, all the boxes are occupied by A's. And if the B, then all B molecules will occupy the boxes. And we know that the system, the entropy of the system is defined to be 0 when it is in a pure form. And then we know that from this form is a pure form. And therefore, the entropy of the system has to be 0. And then we can also use the other definition, one of the definition of the entropy. Let's use the probabilistic definition of the entropy. And then according to this formula, we know that it's defined to be minus nkb sum of I equals 1 n pi ln pi. And based on this formula, that we know that the pi is 1, which means the ln I will be 0, and just ultimately makes the entropy 0. So you can use just the intuition of how the system is pure form and then leads to 0 entropy, or you can use a definition. Part B. So in part B, we are interested in how this formula is true in both using the statistical definition or probabilistic definition of entropy. And just for the simplicity of the question, just to make the question simple, I'll first go over the probabilistic definition of entropy and how is that related to this formula given above. So in part B, that we're given that the delta S is given as nkb xa ln xa plus xb and ln xb. And we know the probabilistic definition of entropy says that is N minus KB PA ln PA plus PB ln PB for this condition. And then the only difference that we see between these two formulas is that on the top we have XB and on the bottom we have PA. So the bottom and the top. But if you look at closely, the XA is actually the mole fraction of AB in the mixture, which means that XA is actually mole of A over mole of totals in the system. And then we actually know that PA is defined very similarly, how this is number of molecules of A over number of molecules of total in the system. And basically the mole, you can just convert into the number of molecules just by multiplying the Avogadro's number. So basically we know that these are, in the end, they're the similar things. So basically after proving the how XB and then BP, PB and then XA and PA are equal, then these two equations should be equal. So now, after we proved that how the probabilistic definition of entropy is equal to the delta S, the formula that we're given to calculate the delta S, now let's look at the statistical definition of entropy and and then like what Byron said about the relationship between the statistical and probabilistic definition of entropy. We know that we use the statistical definition of entropy to actually to derive the formula of the probabilistic of definition of entropy, how we use the Stirling's approximation. ln W is actually equal to n over n. More it's closer when n is large. And then we use this formula to approximate the ln W. And then in the end, we get the probabilistic definition of entropy. So by the saying, because we know how to prove that statistical definition is equal to the probabilistic definition of entropy under the condition that the n is large, then we can also prove, because the formula given as delta S is equal to the probabilistic, then the statistical definition of entropy also has to equal to the delta S formula that we are given above. So part C. In part C, we are asked to calculate the difference in chemical potential between the state 1 and state 2. So we are moving from state 1 to state 2. So we are trying to find the difference. So it will be in delta mu, and then it is mu final minus mu initial. And then because we are moving from 1 to 2, state 2, it will be mu 2 minus mu 1. And then we know that from the condition of the question that is basically the mu when A is a 1/4 and B is a 3/4 of the system minus delta U A 0.5. And then from the lectures that we define the chemical potentials to be so having these three parameters being constant, we are looking at the change of delta G over change of number of molecules. So in the end, we can just interpret this formula as just free energy per molecule. So now, because we have to calculate the free energy. And the free energy is delta G is defined to be delta H minus temperature of times a delta S. And then we know that energy is not so heat is not released in this condition. So we assume that delta H is 0. So it's going to be minus T delta S. And then so we're going to use this formula above, is that the changing chemical potential is basically minus T delta S over number of molecules we have, using this definition above. So now let's expand this formula. Because we are given that A is 1/4 and B is 3/4, so it's really convenient to use a probabilistic definition of entropy. So we're going to use that formula. So moving everything outside, and we're going to use the probabilistic definition of entropy to calculate, and it will essentially be okay. So now if you do the calculation, you should be able to get the number. And before we do the calculation, you can make some intuition about how the answers will turn out. So we're moving from state 1 to state 2. And then we know that this one is 50-50 in terms of the constant, how many molecules we have for A and B. And this one is 25% and 75% for A and B. And based on what Byron said, because we have an equally mixed amount of A and B compared to the state A, this one will be more favorable. Therefore, that we will expect the chemical potentials to be positive, not negative.
I
Okay.
have a question.
Yeah.
I have two questions. So one, when we're putting in the probabilistic definition, that means that in our calculations, we need to convert all the mole fractions we would normally put, like multiply all of them by Avogadro's number, then put them into that equation, and then multiply everything by negative T over N, right? Which N would just be 1 times Avogadro's number in this case.
Oh, okay. So the probabilistic definition of entropy is defined to be minus NKB because we have N on the bottom, N will cancel out. So what you get in the end is we have a 2 minus sign, so it'll be positive KB T ln pi, and this one you have to find the difference for the state 2 and 1. Is it clear?
No. I guess like my question is like when we're putting in the values, I just want to double check. Like for PA, it's the mole fraction of A times Avogadro's number, right?
Mole? Can you repeat the last part?
So we're given a mole fraction, XA,
Right.
which is like 0.25. When we're
Right.
putting it into the equation, do we have to make sure to multiply that by Avogadro's number?
In the end, it's going to be the equivalent because XA is mole A or mole total, right? And then we can multiply molecules over 1 mole times 1 mole and in the end, because these cancels out, basically it's going to be the same thing. So the PA and the XA are equivalent. So you're going to use the PA as XA. So PA is going to be 0.25.
Okay, I think I'm just making a math error then. Okay, and then I guess my second question is, like, in the problem, it says state 1 mole fraction of A and B is 0.5 and state 2 mole fraction of A is 0.25. Right? So was there like an update or something, or?
So you mean this part?
Yeah, so for state 2, XA is 0.25, right?
Yeah. So because you know the mole fraction of A and B are equal, it must be half because there's no empty boxes, right? And this one.
Okay, I was just clarifying.
And then for A, and then B has to be 0.25. For the 7.5, my bad.
Okay. Thank you so much. Thank you.
Any other questions? Okay.
For B, I have a quick question.
Oh, yeah. For B, yeah.
Yeah, can you clarify again how we can equate the probabilistic and statistical definition again?
Okay. So basically, that's what Byron has covered. But let me just cover it again then, very shortly. So we know that the statistical definition of entropy is defined to be the KB ln W. And we define the W as n factorial of NA factorial or MB factorial. So for this case, so for other cases, we have other molecules C, D, this one will extend, but for this case, it's gonna be A and B. And then we're gonna use the Stirling's approximation to approximate the factorial, because factorial, when the number gets really high, is really hard to calculate the number. So Stirling's approximation states that ln is gonna be very equal, approximates the n. So basically, this expression will approximate the factorial of natural log of the n factorial under the condition that n is large. And then we're gonna plug this one into W. And then from there on, so it's gonna be, so this one is very similar to the ln W. So we're gonna substitute the ln W using the Stirling's approximation, and after that it's just all algebra and then just simplification, and in the end you should get the probabilistic definition of entropy.
Okay, thank you.
And then actually you can actually see the whole the algebra all the simplification of this expression in a lecture week 2 on page 18 up to like 23. So you can just refer to the lecture slide how this calculation has been performed, and it takes pretty long time to show you right now. And yeah, is it clear?
Yes, thank you.
Any other questions? Okay, so it will be now on question 4.
Okay, I can share my screen. Can everyone hear and see this?
Yes.
Okay, so question number 4 asks us to consider a system similar to that in number 3, except that now there's a difference in energy between A and B, and there's no interaction between the molecules. And we're asked to calculate the difference in molar energy, or delta U, at equilibrium at 300 Kelvin if the mole fractions are 0.25 for A and 0.75 for B. So for this problem, we can calculate the equilibrium constant for the interconversion between A and B, because that allows us to calculate the difference in energy. So if we look at the interconversion A to B, the equilibrium constant would be the concentration of B over the concentration of A. And that's equal to e to the power of negative delta G over RT. And we can relate the molar energy delta U to the standard free energy delta G, because looking at this equation, we have delta G equals delta H minus T delta S. And from part A in number 3, we know that the difference in entropy between from going from A to B is 0. So we have that delta G equals, so we have that delta S equals 0, and then delta G equals delta H. And because we're working with constant pressure and volume, and delta H equals delta U plus P with a delta V term, this P delta V goes to 0, so we know that delta H equals delta U. So in this case, because we have a constant volume, delta G is equal to delta U. So now we have a way to relate the equilibrium constant to the molar energy that we're asked to calculate. So again, because the equilibrium constant is equal to the concentration of B divided by the concentration of A, and we're given the relative fractions of A and B as 0.25 and 0.75, we can easily calculate the equilibrium constant. And then we can use that to solve for delta U, because again, we know that delta U equals delta G in this situation. So if you could take the natural log of both the equilibrium constant and the right-hand side of the equation, we get that the natural log of the equilibrium constant is equal to negative delta U over RT, and you can rearrange it so that you can have an expression to solve for delta U. And we're given that the temperature is 300 Kelvin, and we're asked to calculate the molar energy, so you can use 2.5 kilojoules per mole for your RT term. Yeah, does anyone have any questions? If there are no questions, we can keep going.
Right. Hey guys, hear me?
You have some feedback.
Sorry. Okay. I don't know if my camera's working or not. Are you guys able to see anything? Okay. Sorry. Okay, I'll just hold this. Okay, so for problem 5, is there still feedback?
Yeah, I still hear feedback. So if you just mute one of your 2 audio sources, I think that'll fix it.
Okay, because my computer should be muted. Am I not?
It's fine.
Okay, sorry about that. Okay, so for problem 5, we are given an expression for delta G of mixing. And we know that delta G is equal to delta H minus T delta S. And we saw in a previous question that delta S is equal to, let me pull it up, negative N KB XA times log XA plus XB log XB. I believe this is part B of question 3. So basically, we're just essentially plugging this formula into the delta G mixing. So that's where we end up getting the T times KV times this expression up here. So then we just need to account for, you just need to account for the delta H term. And since we know that there's an interaction between the A and B particles in this scenario, we basically see that the delta H is equal to N, sorry. Yeah, it's N gamma times XA XB. And we, if you want to figure out just to set up the problem, since we know that delta H is in units of joules per mole, and we know that XA and XB are both unitless, we can see that the units of gamma must also be in terms of joules per mole. Any questions so far with that? Okay, if not, then there's one other bit of information that...
Sorry, for delta H, what's the second variable? It's kind of hard to see for where the x's are as well. Is that an x in the exponent for the A?
No, it's XA times XB.
Okay.
Yeah, it's the same thing that's given to you in the problem.
Okay.
Yeah, and then the next thing that you want to know for the rest of the problem is that if you're looking at mole fraction versus delta G of mixing, anywhere you have a stable point where the delta G settles, this is somewhere where your mole fraction is going to stabilize. And then if you have somewhere where it's a hump that goes above zero like this, it's not going to be able to stabilize. This is technically an equilibrium point, but it's not going to stabilize there because it's an unstable equilibrium. So that'll basically cause it to settle at whatever values it ends up creating down below, and that's where your mole fractions will end up settling. And so this will be useful for when you guys are doing the problem in the next part of this. Any last questions about that? Or else we can move on to the problem itself.
Oh, so for the graph on the right, it will not stay at that top point?
Yeah, that's what I said.
Oh, okay. So what does that top point represent then when it's positive?
Yeah, so basically, since the derivative of the curve here is equal to 0, if you manage to have no perturbances whatsoever in your solution, you could theoretically have it stay still at that point. But since most solutions aren't perfectly still and not unchanging, then any disturbance will cause it to go down either side into the valley and cause the solution to equilibrate at either side. Does that make sense?
Okay, thank you.
Okay. If there aren't any other questions, we'll move on to the problem itself.
All right, can everyone see my screen? All right, so first question, we already went over what the delta G mixing is before, and then the important thing to remember is that XB is equal to 1 minus XA for mole fractions. The first part asks you to calculate the delta G mixing for 5 different values. And then this can be done with a handheld calculator or online or on a Python script. And then once you do that, you'll be able to put that into this table and then graph it. For part B, they ask you to do the similar thing, except instead of having gamma equals 0, you'll have gamma equals a non-zero value of 3 kBt. And then they ask you to do a similar thing with 11 points now and to graph that. And then if you were to graph that, you would get a figure like this, where a couple important things to note. On the left is the graph where gamma is equal to 0. On the right is the graph where gamma is equal to 3 KBT. And the mole fractions on the x-axis, delta G mixing is on the y-axis. And the two graphs do not have the same spacing for the y-axis. And then, so the important points for the left one is that there's only one minimum in the center at 0.5 for the mole fraction of A, which means that it's most stable when the mole fractions of A and B are equal. For the graph on the right, there are two equal minima positions around 0.1. And then this signifies that it's most stable at 0.1 mole fraction of 0.1 for A and a mole fraction of 0.9 for B, or a mole fraction of 0.9 for A and a mole fraction of 0.1 for B. From the lecture slides from week 3, you should know that the existence of two equal minima signifies that there can be two coexisting phases, which means that there should be phase separation for the graph on the right, or for the model on the right, but not for the model on the left. To better understand what it means to have what gamma actually is and how it affects the energy and how it affects phase separation, you can remember that gamma is a measurement of the difference in energy between the interactions of pure types, so like an A and A interaction and a B and a B interaction, and mixed types, which is an A and a B interaction. So a positive gamma means that that pure interactions are more favorable than the mixed interactions. So if we were to change the gamma value, you would find that this is what the result would be. So looking at where the minima occur, with 2.5, it occurs closer to 0.2. With 3, it occurs closer to 0.1, and with 3.5, it occurs closer to 0.05. The actual values are important, but what you should be taking away from this is that as you increase the gamma, the mole fraction where it becomes stable becomes more extreme. And then given that you know, given what gamma signifies in terms of interaction energy, and knowing that increasing gamma means that it becomes more stable when there's more pure type of A or more pure type of B, this should help you understand how phase separation is affected, and hopefully help you understand why the molecular explanation for why phase separation occurs. Does anyone have any questions, or does anyone want to see the first graph or anything?
I'm sorry. I'm just having a little bit of trouble conceptualizing delta G. Why is the minimum delta G preferred over, let's say, the maximum point?
Okay, so yeah, a minimum delta G would mean that it would be thermodynamically favored, so it would be spontaneous in that direction.
Okay, thank you.
Does anyone have any other questions?
Can you go over 5A again?
So 5A is when gamma equals 0. So the only part of the equation of delta G mix that you would have to account for, the only one that you would have to account for is this first part of the entropy one that we covered before. Plugging the values into that one, you would obtain a graph that only has one minima, the graph on the left here. And this makes sense because entropically, it's most favorable when the mole fractions are equal. So there's like more possible states, more possible microstates to be in.
Okay, thank you.
Can you explain again how to tell whether they'll phase separate or not?
Yeah, sure. So I think in the lecture, he talks about it in week 3 on like page 10 or 11 or so. So if you would like to know more after this, you can look there. But the existence of 2 minima, where the minima will not be both at 0.5, means that at some point, there's a mole fraction where it is more stable for there to be more AA or more BB than there is for it to be AB. So this means that there should be some part in the solution where it is favored to have more A's in that area than there are for B's. So there's more of those AA interactions. And it's similar in case of B's, where it's more favorable for there to be more BB interactions. So there's likely going to be more B molecules in the area than there will be A molecules. Now this means that those two types of molecules can phase separate, and then it will satisfy that the favorability by grouping all the A's in one side and grouping all the B's in one side. Does that answer your question, or?
Yeah, thank you.
Okay.
This is just a funny question, but oh, sorry for the background noise. A funny question, but playing with the graph, it looks like changing gamma, there's a point at which there's this flat region. Is that right?
With which gamma value?
It should be when gamma equals 2 kBt.
I was on mute. I'm sorry. Never mind.
Does anyone have any final questions?
Okay, someone else has a question in the chat about this problem. So when a system undergoes phase separation, will it reach to the lowest the two lowest points of the curve.
Could you repeat the question? Sorry. Was the question that?
So when a system undergoes phase separation, will it reach to the two lowest points of the curve?
Okay. So this equation or this graph describes the mole fractions where it would be most favorable. So the solution would ideally reach one. So each phase would only be on one side of the graph. So the phase that is predominantly B will follow the curve to the left side, and then the phase that is predominantly A will follow the curve to the right side. But the solution, so like no one part of the solution should be in both sides, because that would mean that it would be an equal mixing.
So just to double check, does equal mixing means no phase separation, right?
Yes.
Okay.
As a follow-up question, so the two phases are the two lowest points. That was regarding the question that you just answered.
Yes. So the two phases would, so the mole fractions in the two phases would be described by the lowest, by the minima values, yes. So in each phase, the mole fraction of that phase will be described by either the left side of the left minima or the right minima. So if no one has any more questions, I will stop sharing.
So there's another follow-up, another question. Does that mean for gamma equals 0, there's only one phase separation point? So do you want to handle it, or I could?
Yeah, I can answer that.
Okay.
So a phase separation is only possible when there are basically two states for the molecules to be in. For gamma equals 0, since we only have one minimum point, which means that the most favorable position, the most favorable state for the molecules to be in is when there's an equal amount of A and equal amount of B. So this means that there cannot be a phase separation because it's most favorable when they're equally mixed. Now on the right side where gamma is non-zero, there can be phase separation because there is a point where it's more favorable for more A's and for more A's to be near each other. So this means that with a greater population of A's surrounding one A, it's more favorable than having an equal amount of A's and B's, which means that more of those molecules will group to one side, and the other group of molecules will group to the other side, which creates your two phases.
So to clarify, when you increase the gamma value, that means that if there is an equal amount of both A and B, for example, in the 3kBT, it would require, there would be more free energy.
Yeah, the free energy would be more positive, so which would be less variable.
Okay, thank you.
Right, so if gamma equals 0, as you asked about, then there's no driving force that would make the molecules prefer their own kind. So if every possible state is the same energy, then you'll want to go for the one with the most multiplicity. Okay. Are there any other questions about this topic?
Yeah, for this question, would n equal 1 or is it a different value?
I guess I'll answer that. So this is in terms of mole fraction. So I don't believe that there's any requirement for big N or little n to be a specific value. It's all the relative amounts. Okay, there's another question. For question 5, what do you plug in for n when making the graphs?
Oh, okay. So, when you actually like write down the values of the graph, they do ask you for delta G mix per molecule. So your actual value would be delta G mix over n. So you wouldn't have to plug in anything for n. Does anyone have any other questions? Okay, if not, I will stop sharing now.
Okay, I think I'll cut the recording.